Okay, hi, my name is Jan Gillespie, and I'm a geologist living here in Kanab. When I started doing the Cottonwood Road Guide with my co-author Krista Sadler, that was in 2007, and I was a university professor in Bakersfield, and the garden spot of California, not really. And all I did was look for ways to get away from there in the summertime. And one of the things I did, even if they didn't pay me, so I get a hold of Carolyn Shelton, who some of you may know, who was working at the Grand Staircase at that time. I just threw an email out into the ether and said, do you need a geologist volunteer to do anything for the summer? I said, would you make a road guide down one of the roads? And I said, sure. And she says, pick a road. And I looked at the geology and I went, that one. That's the one I want. And I hope that as I give the talk today, you'll see why I picked that road. So, pay attention. Okay, so obviously you guys know where we are. We're here in Kanab, Page. We're in National Park Wonderland, Bryce, Zion, Grand Canyon, all around us. Who could ask for anything more? There it comes. And in between all these wonderful national parks is our national monument, the Grand Staircase. And the Grand Staircase comes in 3 different flavors. The Escalante Canyon section up here in the northeast, Caparowitz Plateau, there from Nate, Caparowitz Plateau here in the section, Dinosaur shout out, Grand Staircase section here in Kanab. Woohoo! Okay, and click it again. Oh, go back, I'm sorry, go back. The reason I like Cottonwood Canyon Road, which runs right along through here, is that it covers the Caparowitz in the south, it runs along the boundary in the middle, and then it runs along the Grand Staircase section in the upper end, the northern end. So you get to experience all these different parts. Okay, now you can go.
Right, here we go.
Okay, so if we look at this in the 3rd dimension, we just looked at it in 2 dimensions. We look at it in the 3rd dimension, we can see all this strata. This is the Colorado Plateau stratigraphic section, from the oldest to the youngest. Click on it for me. The Grand Canyon tells us all about the old stuff, the pre-dinosaur era. Click it again. Bryce Canyon tells us about the post-dinosaur stuff. Up here, the young stuff. And click again. And Grand Staircase tells us about everything in between. So primarily the Mesozoic, the dinosaur era. Next slide. So we're going to focus for this talk on these 2 parts of that Grand Staircase. We're going to focus on the Jurassic and the Cretaceous. The Triassic's not exposed along Cottonwood Wash Road, so we're not going to talk about that. We'll talk about these 2. And what we see here is in the Jurassic, for instance, the older of the 2 periods we're going to talk about, we have a lot of red and white sediments, and that indicates an arid climate. And we'll talk more about that later. In the Cretaceous, we changed to gray and brown, and that's a swampy, humid climate. So we see this big climate change over time. Next slide. This is what this area looks like from space. And one of the things that should jump right out at you, here's 89 for reference. One of the things that should jump out at you is this thing right here, which I just find fascinating. That's the boundary. That's the East Kaibab Monocline, as most of you probably know it. And we'll be talking about that a little bit here too, because that features pretty prominently along the road. Next slide. So here's Cottonwood Wash Road. Here's 89. We're going to start down here in the south, going through the Caparowitz Plateau part of the monument. And you can look on here and you can even see that gray and brown here in the Cretaceous, and that red and white over here in the Grand Staircase part. Then as we turn, the road goes up the boundary and then heads over here into the red and white, which we'll end with. Next slide. Okay, and this just kind of shows it a little more graphically. Next slide. Okay, we're going to start down here on the Caparowitz Plateau, and we're going to look at the geology along this section of the road. Next slide. So we're looking at this gray and brown. Here's what you will see. Here's our road right here. And first thing we're going to look at is this gray layer right under here. This is the Tropic Shale. And it shows up right here in our strat section. It's this big gray interval. And this is really the only full-on marine section that was deposited in an ocean that we're going to see out here. And this is, if you could look at the Earth from space, if we had a spaceship during the Cretaceous, which of course we didn't, we would see this shallow arm of ocean that connects the Arctic and the Gulf of Mexico. Because unlike today when we're about 5,000 or 6,000 feet high, we were close to sea level at that period of time. Kanab is sitting, or Cottonwood Wash Road Kanab is sitting about right there on the western shore of that ocean. We have all these mountains here to the west that are going to become important. The continent is moving this way, it's crashing into the Pacific plate, and it's rumpling up all these mountains. And eventually these mountains erode and start shedding sediments into that ocean, as we'll talk about in a bit. Next slide. If we could go back and look at what was going on the ground in here, we'd see animals like this, which we wouldn't want to be snorkeling around. This is a short-necked plesiosaur eating a turtle. And what your clients would probably like to see, they're probably not going to see any plesiosaur bones. That's pretty rare. But what they do see a lot of along here, and we show some stops in the guidebook, Krista and I, you'll see a lot of these oyster beds, and a lot of people have never seen fossils really before. And so if you can show them things like this, they get really excited sometimes, because it's like, well, there's like 100-million-year-old oyster beds, which is kind of cool. Next slide. As we move up in time, we start getting up here into the Straight Cliffs and the Wahweap Formation. And above that is the Kaparowitz, where the big dinosaur finds are, but we don't really see that along the Cottonwood Wash Road. That's farther back in. And so here we're looking at these brown layers, these big cliffs and stuff that we see up on the top. And what's happening here are finally these mountains are shedding sand into that ocean basin and creating these big deltas that are starting to fill the ocean with sediment. So we end up with this big swampy shoreline that looks a lot like modern-day southern Louisiana down south of New Orleans. And this is what we might have seen if we were to go back there and look at the types of animals and landscapes. Again, we're right at sea level. Next slide. Okay, we're going to move along a bit. In the library, I gave a 40-minute talk. I've had to trim it down here a little. But we're going to move on to the boundary right here, the East Kaibab Monocline. Next slide. And this is the centerfold of our book. I like to bill it as a naked grand staircase centerfold. You pull it out, and you can see this, see everything under here. And you notice that, like most of the Colorado Plateau, the layers throughout most of this area are flat, or maybe they're just tilted a little bit. But along this boundary, everything goes crazy. Here, this side of this fault underneath of us has been pushed up, and all the younger sediments like the Kaparowitz and the Wahweap have been eroded away. We don't see them till we get way up near Escalante. And this side's dropped down, so now all these sediments up here, like the Navajo and the Kayenta, they're down here. We could drill down to them. They'll be exposed sometime in the next few million years. But this thing has pushed this up, pulled this down, and this fold is like a tablecloth hanging over the edge of a table. We call that a monocline. And that's what we're looking at here, and it's just fabulous when you go down the road, as most of you know. Next slide. It looks a lot like this. If we're in the side, happen to be on the side of the boundary that's in the grand staircase, we look like a candy cane. We're kind of red and white. This is Santa Claus Rock, by the way, because it looks like Santa Claus with a pack on his back. And this, if you can give it one more click, I think. Yeah. And here you can see from the air, here's Cottonwood Wash Road right here. And you can see all that red and white on the grand staircase side of the boundary, and all this gray and brown in the Cockscomb on this side of the boundary. They often call this the squeeze and this the Cockscomb. Next slide. And what I wanted to do with this is put it in perspective. We had been looking at just this square when we looked at this area. Now I've blown this thing up on Google Earth, so we're going all the way down to the Grand Canyon. And this feature, I just wanted to point out that this feature we're seeing here is a lot bigger than just this area. It goes all the way down House Rock Valley Road. You guys all go down there all the time to the Wave and White Pocket. It's the same feature. You can see all those beds tilted towards the east along there. It goes all the way down to the Grand Canyon, and when you get off rafts down here, you can go and see it as the Butte Fault, which was actually active during the Precambrian, so before animals actually even developed shells. So super old feature. Next slide. Finally, we're going to get up here onto the grand staircase. We're going to bypass Grosvenor Arch for the day. That was my title slide. I should have pointed that out. We're going to go past that, and we're going to head this way past Cottonwood Basin and up to Cannonville. And we're going to be looking at this red and white section in the Jurassic, the arid climates. So here's our red and white, our Vermilion cliffs, our white cliffs. There's some gray cliffs back there, which would be Kaiparowitz, and then this is Bryce, of course. But this is the section that we're looking at right here. Next slide. Again, if we're up in a spaceship during the Jurassic and we're looking down, notice we don't have an ocean anymore. We're before that. Okay, this is an earlier period of time. And we just have this big sand sea in here, and everything out here is like, out here we have like saline arid tidal flats, like in the Persian Gulf today. We've got these big sand fields like in Saudi Arabia, so we're actually a pretty good analog is the Middle East for the Jurassic out here. And we're sitting right in this box around Cottonwood Road. Next slide.
Where's the equator on this?
Oh, actually, we're pretty close to the equator here. There's the equator, if you know anything about geography, I guess you'd call it that. The equator is really tropical, but as you move north and south from that, you come into this thing called the horse latitudes, where the climate becomes very arid, and that's where most of the world's great deserts are. The Sahara, the Atacama, all those deserts we know pretty well. And that's where we were sitting here, is we're just in those horse latitudes north of the equator. Good question. And this is what it would have looked like on the ground. Here's these big sand dunes migrating along, and in between the dunes, we'd get these oases that were drawing all this wildlife, dinosaurs, pterodactyls, whatever, looking for food, looking for water. Next slide. So when we look at, in this case, the Navajo sandstone, here we're looking at a fossil sand dune. So it's like the dunes we saw in the last slide, but we're looking at one right here that's been fossilized. And you bring up, just click again. What happens with these dunes is that as the wind blows, in this case from right to left, it erodes and sand off the top part of this dune on the side that's upwind. It carries it to the top of the dune, and then it avalanches down the front and makes a little layer. And as it does that, the dune moves slowly downwind like that. So every one of these little lines you see are those crossbeds, we call them, that show us the direction the dune is migrating, and also tell us the direction the wind was blowing 190 million years ago, which is pretty fabulous. That can impress some clients right there. Next slide. In between those dune fields, in the oases, we have an area that dries up during the dry season, gets wet during the rainy season. And so it gets muddy in those lakes. It's also a good place to find tracks, as I'll show you in a bit. And we get all these mud cracks. Now these are modern mud cracks. But here, the bed below this one, we're looking at the bottom of a bed that's hanging over us. And look at these lines making these little polygons in here. These are fossil mud cracks from an ancient oasis that was out between the sand dunes. It's just inside this little red bed right in between this sand and this sand up above it. Next slide. A lot of times we see these from the side. I'm sorry, today I tried to take a picture of mud cracks up on the Kanab Trail, and I couldn't get them mailed, so I had to use some from Wyoming. But there's some really good ones out at Shepherd's Point, just west of Cockscomb. But anyway, you see these little guys right here. I've got yellow arrows pointing at each one. This is looking at a mud crack from the side. So this bed had a mud crack in it, and these little open spaces in here filled with sand, and that filled up these little open spaces. So we're looking at the mud cracks from the side. And you'll see some of that out there too if you look really closely.
You see it in the Navajo, or do you see it in the Entrada?
You see it in the, in my case, out here I see it in the Kayenta, right on the Kanab Trail. It used to be Squaw, I'm trying to remember, call it Kanab Trail. You also see it really well up in the Entrada Formation, up at Shepherd Point. They're beautiful there. We'll take the field trip out there on on not this Saturday, but next Saturday, and look at some of those. But these particular ones are in Wyoming, but that's the only one I could grab in time to get in here. But if you see those, that's what they are. And typically, fossils don't preserve well in an arid climate. So we have to mostly look at tracks in these areas because it's just dry, there's too much oxygen, bacteria chomp away at things and they just decompose. So this is Flag Point. A lot of you might recognize it as Flag Point. So you can see the Growlator tracks. This is out at 20 Mile, out at Escalante, where you can see the dinosaur tracks in the Navajo. This is in the Kayenta. This is in, so the red beds. This is in the Navajo, the white beds, and you can even see their tail drag in between the tracks, which is really cool. And I believe the Watershed Symposium also is taking a field trip out to that site on Friday afternoon. Mine is Saturday morning, this one's Friday afternoon, so I'm going to go on that one too.
That's Entrada.
This is Entrada. I think this, that's right, this is, I'm sorry, this is the Escalante part, member of the Entrada, I think. Yeah, sorry, thanks. Entrada and Kayenta. And that takes us to the end of the trip. We're in Cannonville now. We can go for a burger or whatever we want now that we've finished with that. And I will open it up for any questions. I talked about sandpipes, and I didn't want to do that because I'd run out of time here, but I did put some slides in just in case. That's what I'm going to talk about at the symposium, because that's where the field trip's going. Yeah, Mel?
I'm a big fan. Can you tell me a little bit about the first edition of your book and the second edition? And if I have the first edition, should I be looking at the second edition, or what can I anticipate? Okay,
like when I wrote the first edition, Krista and I wrote it from the south to the north, and then they decided they want to turn the book upside down and have it go from north to south. So I think you'll find this, especially the north to south part of that, is going to have some really wonky mileages in some spots. This new edition should take care of that. We've changed the names to reflect the changes in stratigraphic nomenclature. The Dakota is now the Natarita. The Henryville is now its own formation, I guess. So there's been a few changes like that.
Is this book out yet?
Oh yeah, it came out. The second edition came out in August.
Okay.
Yeah, because the first wasn't a double flip.
The first was like an upside down.
Yeah.
This one is not upside down, right side up one. So.
Yeah, that's a different.
But yeah.
Oh, okay, got it. Got it. Sorry.
Krista's got cool books about dinosaurs too.
So Krista had some cool stuff to put in about that. So yeah. And the first one, she mostly did the walks, and I mostly did the road. And so this one, we both kind of put our heads together on. So, and then Amanda Boston was our editor. So I think she had a big hand. She really deserves a shout out because she really did a good job.
What's your favorite formation?
Oh, wow. Wow. I think the prettiest formation is the Henryville, when the light hits it just right. There's not very much of it, but it's pretty. But I'd have to say my heart belongs to the Navajo. Yeah.
I have a lot of questions. Maybe I'll talk to you afterwards just for like 5 minutes. Could you maybe go into how two phenomena occur? And you see this in Zion a lot, how we have the red-white bands on the Navajo, and then also a couple people have tried to explain this to me, and I'm not sure if I get it exactly. Maybe you have a good explanation about the blind arches and how they might form.
Oh, I'm still kind of clueless about those two. You're talking about the ones that are just alcoves that haven't gone all the way through? Yeah, I know it has something to do with freeze-thaw issues along curved fractures, and there's a lot of physics to it, and the fact you've got the arch form, like the keystone sorts of things, but I'm not your girl on that one. Now, the red and white I can help you with. There's a lot of iron, oxidized iron in say, the Navajo sandstone, and typically what happens, and it's oxidized, that's why it's red. So typically what happens is when groundwater flows through the more permeable parts the Navajo, it will pick up some of that iron and carry it away and leave those layers bleached and white. Typically the ones that are more red were a little bit what we, in the oil industry when I worked there, we called tight. They are a little less permeable, and so the groundwater doesn't move through those quite as effectively. Instead, it tends to go around them. So the iron gets left in those beds, and they're white. So that's a process that's influenced by groundwater flowing through those rocks at a much earlier time when it was underground.
Are there more springs in the white layer because of that?
Yeah, what'll usually happen is the groundwater will settle down until you get to an impermeable layer. It'll sit low in either the white or the red. It'd probably prefer the white. But once it hits one of those oasis layers, which are muddy, that's where it stops. And it sits there, and then it runs along the top of that one until it finds an opening to the surface, and there it comes out. So it's really looking for those oasis beds. And when you're up in Kaibab Canyon, for instance, as you're driving north on 89, you'll see these big limestones. They're rough, and they're probably yay thick, and they're just angular, and it hurt like if you slide. We call them tear pants weathering because they're sharp on the edges. And those are lake limestones from the oases. And you often see springs coming out on top of those too. And you also see a lot of tracks in those because they were lake bottoms. You got first.
Back to the oxidation deal. So the clients are always asking me, how long after the time of deposit do we start to get things like concretions and oxidation forming?
Well, all those things happen when you have groundwater, so they had to be below the water table. Okay. And so, they sunk below the water table probably very soon after they were formed. And for instance, a lot of the deformed beds that we see at places like White Pocket would have had to happen before they had actually hardened and turned to stone, but they were still full of water under really high pressure. And that's sort of the part I'm going to talk about a little more in Escalante, just because I couldn't give the whole talk here.
Yeah, hey, what's up with that?
Sorry.
But yeah, so for instance, in order to make a Moki marble, you have to have, there's something in that sandstone somewhere. Maybe it's a bone fragment or just some piece of something that's got a little different chemistry than a quartz grain. And the water flows through and is carrying chemicals within it, usually iron or manganese. And it comes along, it hits that thing, and it precipitates out as a reaction front. And then more precipitates out, just all around that one little grain until you finally run out of reactant for it to form. And then the water just flows around it and out. But it leaves that marble sitting there for us to find 100 million years later or more. So how long ago? It had to be below ground. It had to be below the water table.
It had to be below water table.
Right.
Got it. Okay. That's a good start.
Yep.
So to kind of piggyback on that, another question is, number one, is our water more rich in iron because of that process?
Yeah. The water we drink?
Yeah.
Yeah.
Okay. I just had a guess asking that.
Unfortunately, I learned when I took the Master Gardener course, our iron is in a form that can't be taken up by plants. It's in an oxidized form rather than a reducing form. So I have to, as odd as it sounds, I have to put iron on all the plants in my yard to make them happy, because I have no mobile iron that they can take up. It's the red stuff, they can't take it up. It's bizarre, but yeah.
Interesting. The other part of that is, I've heard that water at some of the springs in the area has been dated to be like 2,000 years old.
Yeah, that's possible.
How do they figure that out? Is that carbon dating?
They can use carbon dating for that.
Is there something alive in the water?
No, it's probably just atoms like carbon dioxide that it picked up as it moved through the atmosphere and worked its way down into the aquifer and carries it along with it. So it could be something as simple as that. But usually it's something that was living beforehand. So it could be charcoal, it could be bacteria, any kind of carbon. Yeah.
So on the Moki marbles, some are oval, some are round, some look like spaceships. I've seen doubles. I mean, is like the water flow impact that? Like what can kind of influence the shape of those, do you know?
Yeah, it could be just the flow pattern of the groundwater. That's what I would guess, but I can't say for sure. It's not my area of expertise, but what makes the shapes. Typically, you like to think of a chemical reaction front as being perfectly spherical, but I guess if the water is moving pretty fast through something, it could elongate it somewhat.
Yeah, I've just noticed in some areas, they tend to be similar. You know, if you find one and you find others, they're going to be more
Same
similar in shape and sometimes size.
Yeah, I would assume it's probably a groundwater flow phenomenon. That's my best guess for that.
I've also heard that there's a magnetic phenomenon with the amount of iron that's in it.
Because it's a magnetite?
Yeah, because of, and that's like why in Boulder Creek you get Moki marbles, and in Calf Creek you get Tholic or sheep.
Oh, cool. Yeah, like people like David Loop, Marjorie Chang have been studying, Marjorie Chan have been studying those a lot more than I do.
Might sound very simple, but about the earthquake cracks, why are some straight and some others like?
Well, they're usually, you mean like vertical versus tilted?
Yeah, and some others like circles.
Yeah, typically they're not, some are curved. There are some curved ones. That's actually not a simple question at all. It really kind of depends on the direction of the force and the zones of weakness in the rocks. So for instance, what'll happen in a rock, if we have a lot of first of all, there's something called joints and there's faults. Joints are cracks that don't move. They're just, the bedding in the rock goes right across them, never moves. So they just sit there still. But if I put a particular vertical stress on that, like if something's pushing it from below, it's going to use that plane of weakness, that joint, and it's going to say, oh, I'm going to break here. And it's going to go boop, and one side's going to go up, one side's going to go down. Now, if the stress is coming more from the side, now it's going to try to push something up and over, let's say. So it'll be a little more slanted, like that. And if it's being pulled apart, one part will slide down the slope. If it's being pushed together, one will slide up the slope of the crack. But we kind of want that diagonal crack to form. So it's not straight up and down, but at a slant. So if I have one that's like this, like my arm, and I pull it apart, this side's going to slide down. And that's what we call a normal fault. If I have that and I push it together, this side's going to slide up and over because it's trying to make that crust shorter. Does that make sense? Is that what you're asking?
Yeah, and what about the little circles? Example in Peekaboo Slope Canyon up on the rock.
Oh, water disruption.
Oh, you're talking like the sand boil things.
Yeah.
Oh, can you go ahead a slide?
Yeah. All right, so you get to see a presentation now.
Okay, yeah, there's one. So, like that. So what we're looking at is like something being liquefied coming up and creating this boil up at the surface, the sand boil. Hit it once again, it might have that's what it looks like in the modern day, in real life. So you might be seeing the bottom part, the lower part in here, because you probably cut it off by erosion. So this top part has been eroded away now. So you're just looking at this thing, this little tube that came up to feed the boil.
You're looking at it like from, think of it like this way, like round in the wall, and then it's been eroded with the slot, as the slot canyon formed. So you're seeing like a two-dimensional, like this up in the wall, where it was like that when it was forming.
Mm-hmm.
That makes sense.
Did you get weird liquefaction in Navajo as well?
Oh gosh, yeah. Go ahead a little bit more. A little more. Oh, I didn't put that one. I took that one out. Shoot. Okay, it's gone. I was thinking of White Pocket.
Okay.
And the wave. I mean, that's total seismic.
That little slot that people call it like the vortex, that disruption in the wall, like next to the wave.
Okay.
Rich manganese.
Yeah. Where it's all like messed up in the wall.
There's so much messed up stuff at the wave.
Right. So when you come into the wave, and then instead of going out through the formation, you go to the right, and there's that little spot right there.
Yeah.
So that's kind of the same thing. That's a boil that happened.
Yeah, well, what you're kind of probably looking at the wave is you've got some of these little little oasis beds separating dunes, or you got just, horizontal surfaces separating different sand dunes. Those things, when they were still soft, fairly soft, were under they had water under pressure. I mean, the sand grains were practically floating on this high pressured water that had nowhere to go. And then an earthquake comes through, and this wave, it just pressures it up as a wave moves through, because it's a compression wave. And it just goes, I can't take it anymore. And it just goes, and it turns into quicksand. Just think of that aquifer under the ground becoming quicksand as the earthquake wave moves through. And when you go to White Pocket and you go to the wave, that's what you're looking at, is you're looking at something that happened probably in an instant, in an earthquake that passed through that area. And there were several of them. It wasn't just one earthquake. But that had to be super saturated with water, and it had to be under high pressure when it happened.
Pretty cool stuff.
I know. There's so much out there.
This is the spot you're talking about.
Yeah.
So,
We stopped there and looked at.
Oh my gosh, look at that thing.
so see how it,
Wow. That's really cool.
You've seen it.
This is right when you turn right? Yeah, I think I have.
it's at the end as it opens up.
That's pretty cool. It's got to be the same.
Yeah.
And it could be coming in at us out of the rock, or have been coming, what's been eroded away. So we could, you always have to remember you're looking at things in 3 dimensions.
Yeah.
Who knows what's still inside that rock that was feeding it, or that was coming from the spot where you're standing that's now been eroded away. So we always have to be thinking in 3D in geology. It's real easy to look at a rock face and go, oh, but then wait, what's going on back in there?
There's some calcium deposits in 3
Okay, thanks guys.